good afternoon. Thanks for coming to class the day after the exam. It's not like we ever learn anything the day after we come, but we'll try. So today we're going to start on a new topic for Homework 7. We're going to be working on Big O. So that is part of computer science because we need to understand how fast functions grow. Because when we write algorithms, we actually calculate how long they will take to run. We wouldn't bother except that some things don't finish running by the time you want them to finish running. So you've got all that time in between when it's running to think about why it's taking so long. So it actually seems a lot more abstract than that. So we're not actually going to take a bunch of pieces of code and count lines of them and estimate the functions. But what we're going to do is learn the underlying mathematics so that we can compare two functions so we can decide if someone tells us how long a piece of code takes to run, two pieces of code, which one should I use in which situation. So toward that end, let me ask you a question. So here are some graphs of three functions, f, g, and h. And let's assume they are the running time for a few different algorithms. And if I have, let's say this is 10 right here. So let's say these are running times for an algorithm. And over here, this is the size of the input. So when we graph the running times for algorithms for input, this is, the y-axis is how many operations have to be done. So that's basically how many times do I bring a command to the computer and have to do something for the number of inputs. If it was a constant, so no matter how many inputs there were, then what kind of function would we have? It would be a flat line, right? Somewhere. So if it was a constant, it would be like that. Okay? And what is this line right here? That's the y equals x line. It's a line, so it is linear. Linear functions basically take about the same amount of time as how many inputs you have. So can you give me an example of a linear function? Something that would be linear for the number of inputs you have. So every time you have an input, you do one thing. What did you say? Adding? Yeah, adding would be linear, right? Because I have to look at all the elements. So I have to do one thing for every element, and each time I can add the running total. Okay? How about printing out a list? Right? Traversing an array? Any of those things are linear. How about sorting an array? And log n is the best you can do. How about bubble sort? It's bad, right? It's bad because it's n squared. So n squared is the running time for bubble sort. Which one of these looks like n squared? G looks approximately like that. Okay, and so if you were going to pick an algorithm, which one of these would you pick, saying that you want it to run the fastest? Okay, so one person votes for F. Why would you pick F? Depending on how many inputs you have. So how many inputs do you have when you pick F? 100. Good. So this is a low running time because it's a low number of operations. In fact, it seems to maybe be like capped, right? It might even be an asymptote to something. So that means even if I get a whole bunch more stuff, I'm probably not going to increase. So every time I add one more element, I'm not increasing very much. Okay? So if n is 100, I would pick F. And if n was 10, which would you pick? Would you pick F? No? You'd pick something less than F, which would be G, or, if y equals X was one of the choices. So this is basically what we're doing with Big O, is However, what we're doing is we're going to assume we're always going to pick for huge numbers of n, because for small ones, we don't care that much. Even if something takes a lot of computation time, you know, I can probably wait long enough. Except maybe this one, right? I don't really want that. Depending on what the units are over here, you might not want to wait that long even for 10 elements. Okay? So this is what we're doing when we look at functions, but we're not very good at like looking at a function and then knowing like what kind of graph it has and which one's higher than the other. So we need to have a procedure, especially for more complicated functions, so it's not so hard for us to look at functions like x squared, x cubed, e to the x, all those kinds of things, and figure out which one would be the fastest. But when we start adding and multiplying stuff together, it gets more complicated. So we need to have a procedure so we can actually tell what the big O of something is. So we have a definition for big O. I bet you were like, oh, I thought we were done with predicate calculus. So let's read this in regular English. In regular English, this says, there are two constants, c and k, so that as long as x is bigger than k, then f of x is less than some constant times g of x. You might want to write that sentence down so you can remember it. We're going to use this a lot. So if someone asks you to show that one function is in big O of the other one, this is what you have to prove. So you're probably looking at it going, okay. Well, let's do some examples. How about n squared and n? So we just looked at the graphs, but now let's look at it with this equation. So which one would be the smaller one? N, so let's let that be f. So let's show that there is a c and there's a k, so that for all x bigger than k, I don't need absolute value because we're positive all the time for these, and most of the time we will be. So I don't mind if you don't remember the absolute values on these because we're going to deal with positive functions. Because when we run code, is it possible to have a negative number of operations? No. What did you say? Best program ever. It would probably be erasing your kernel, so it might not be the best program ever. I don't know. If it was magically doing that, it might magically do some other stuff you don't want it to do. So I don't know. I probably wouldn't like that program very much. Okay. So I shouldn't use x's. I should use n's because I have n's in my function. So we got a question during the test last time and said, oh, you said we could use 3 divides p squared implies 3 divides p. Does that mean we can also say 3 divides q squared implies 3 divides q? What is the answer to that question? The answer is yes, because letters are just letters. If they have the form, it doesn't matter what the letter is. You can switch the letters. Remember, you can use teddy bears and hearts for letters. I'm going to start doing it if you guys don't get it soon. Okay, so yes, if you've proved it for one letter, it works for all the other letters. It doesn't matter what the letter is. Okay. So now this still looks like Greek, even though we've put some better functions in there that are more specific. So what this means is we have to find some constants, c and k, so that if n is bigger than k, then n is less than or equal to a constant times n squared. The first thing I like to do if I'm just given two arbitrary things, is let's say actually that this was 5n instead. So I'd like to get rid of as many constants as possible. So I'm going to let c equal 5 so I can divide them out. So you get to pick c and k. So this is the most confusing thing for most students. But when we look back at our graph, if I just want to show that, you know, when n gets really huge, that I can multiply a constant times one of these functions and make it bigger than the other one forever, always, you can pick how far out you go with k. So k is the vertical bar of x, like where do I get to pick it, and after that, one of my functions is bigger. And then you also get to pick a constant that you multiply your bigger function by. The reason is that constants don't make much difference when you have like millions of inputs or hundreds of thousands. So we can get rid of constants. Yes? The k goes exactly right there. So the k is a starting value. So you remember when we were doing induction, we were proving some things like n is bigger than something? That's what we do. Is we pick the starting point when we want this inequality to be true. All right, so now we're going to let c equal 5. So I don't need a there exists anymore. Now I need a there exists k. I do still need that one because I've already set a value for c. So proving that's going to be the same thing as saying n is less or equal to n squared. All right, now we get to pick k. I like to pick k equals 1. You can pick anything you want, so that's why I'm actually going to give you, I'm giving you guidelines for how to pick them, because that's the most confusing thing. So if you just pick c equals 1, I mean c equals something that lets you cancel out some constants, and pick k equals 1. So now we're going to say for all n greater or equal to 1, this is getting more understandable, right? As we pick our values, we can start to understand what the heck that means. Now, can I prove this? For all n, where n is greater or equal to 1, is it true that n is less or equal to n squared? Yes, it is. Easy to prove, right? Because I can divide both sides by n and get 1 less or equal to n. And oh my goodness, that's the same equation as that. So therefore, this is true. So all I did was divided this by 1 on both sides. And now I've actually shown that n, 5n, is actually in the big O of n squared. So that's how we write it. So this E, it's like a C with a dash in the middle. It's the Greek member symbol. So big O is actually a set. So it's a set defined by a function. It's the set of all functions that are less than or equal to a constant times the function in the parentheses. So the set big O n squared is like 10n squared, 100n squared, 1000n squared, n squared plus n squared plus 7, minus n squared, because we do absolute values, but we don't care about those. It also includes much smaller things, like the function f of n equals 2, and 5n, and 5n plus 10. But it doesn't include n cubed, for example, because n cubed grows faster than n squared. So n squared multiplied by a constant can never be an upper bound for n cubed. Okay, let's try. Let's try and see if n cubed could be in big O of n squared. So if it was, this is what I'd have to prove. Okay, what I would have to prove is there's a constant, there are two constants, sorry. Now remember when we did our predicate calculus, if a variable comes first, it can't change based on anything else. So once we pick C and K, n can get as big as it wants. That's really what's going to be the trouble here. So if I pick some values, that's where our trouble is going to be. So like I said, I usually pick K equals 1. I pick C equals 1 if nothing else needs to be there. So in that case, we'd be proving for all n greater or equal to 1, n cubed is less than or equal to n squared. So for n equals 1, what do we get? 1 cubed less than or equal to 1. Now, if I wanted to prove this true by induction, I would assume what? All right, so we can actually find big O's by induction. So what we need to do is write one of these sides in terms of one of the assumed sides. Or we could also make this problem easier. So when you do an induction proof, you don't have to do it the way it's formulated. If it's much easier to do some other way, you can also do that. So I would divide n squared out of both sides. Right? So that would be n less or equal to 1. So we can't even do that, right? Because n is greater than or equal to 1. So this is only going to work for n is less than or equal to 1. So I don't even need to do the induction because it's not going to work, right? It's not going to work for one more bigger yes. That's a great question. Let's see. I don't think the answer is yes, but it might be. I'm not sure I could prove it for everything. So I wouldn't assume that, except for functions I give you on the test, I would. Let's put it that way. So for most functions that you're going to have for like running times for algorithms, probably yes. So I'm just going to say probably yes because I don't want to take your time in class with right, so if I have a sine function, yeah, we'll just say this is y equals 1. So you can have a wavy function, but usually if I multiply it, but let's say I was going to compare it to some other, so you were talking about a linear function? Right. You mean something like this? Right. The thing is that if I'm going to compare these two functions, I can multiply this one by a constant. So whatever number this is at, I can move it up higher. So that's what multiplying by a constant does, right? So this is if this is y equals 5, you know, I can multiply it by 5, and that can be y equals 25, right? So I can multiply things so I can move them, you know, sort of magnify them, but I can't change their shape. So if something could be bounded with a flat line, I can also bound it with a sine function because I could just multiply the sine function by enough and move it up. Are they in the same big O? That's a good question. So let's see, probably yes, because I can bound a sine function with two of these. So I would say that the sine function and a linear function are in the same big O as each other. So let's look at that. That's okay. Yeah, you can. You can add things too. So let's see. Let's do this. We're going to say is x in the big O of sine of x. So like I said, I like to pick my constant 1. Actually, let's do the other one, which is easier. Let's do this one, and then we'll do the other one. So it's really easy to show this. It doesn't even matter what x you start at. So we'll just start at 1. Sine x is bounded by what? It's bounded by what? 1? Oh. Yeah. That's good. So it won't keep trying to focus on my hand? Thank you. That's so smart. Okay, so what's sine x bounded by? 1, right? So well, that's less than or equal to x, right? So now I've just proven that sine x is in the big O of x. Actually, we were trying to look at linear functions, so, flat functions. So actually, we need to put it in less than or equal to 1. So that's fine, because that's what we wanted, because that's less than or equal to 1. So now we want to see is 1 in the big O of sine x. So is there any way I could multiply sine x by a number and make it always be bigger than 1? No, why not? Because it always goes back to 0, right? And when you multiply 0 times something, it's always 0. So this is not possible. So even if I had a C right there, so that's not going to work. So we don't do that, actually. So we don't actually add things for big O. So you could add a constant, and it definitely would be, but that's not what we do. But normally, we're also not looking at functions that go back down. So sine x is not usually a function that I look for the number of operations I have for the size of input, because they don't ever go down to 0. So they're usually monotonic, so we don't actually usually have this trouble. That doesn't mean something couldn't wave, but it usually doesn't wave back down to 0. So it's only because that happens. So if it happened to if it was already added, if I already had something added to it, then we could do that. Okay? Okay, so the main thing you need to be able to do, there are two main things you need to be able to do. If I give you a function, you should be able to tell me if it's in the big O of another one. And we also want to estimate the smallest big O function that we might look at for something. So, for example, let's say we have something like this polynomial as our runtime. the problem might be give the smallest big O estimate for f of n. So I have a procedure for doing this. Let me see where it is in your packet so I can tell you. Okay, so the procedure is whenever you have a sum and you're trying to figure out the smallest big O estimate, figure out what the largest term in the sum is. What's the largest term? N squared. Now replace all the terms with that, but leave the constants there. So we know that f of n is equal to n squared plus 3n plus 7, and that's definitely less than or equal to n squared plus 3n squared plus 7n squared, as long as n is what? If n is greater than or equal to 1, right? If it was 0, that wouldn't work. So automatically we've picked one of our constants there. So now we're basically trying to get an upper bound of f that's as close to f as we can get. So let's add all those terms. That's going to be equal to 11n squared, right? So we've actually just now done a proof that f of n is less than or equal to a constant times n squared. It's a little proof, right? We didn't have to do very much for that. But it is a proof, because this always works. So anytime you have a sum, figure out the largest term in growth, like if n was very large, then replace all the functions with that, all the functions of n with that, and then you write down like what your minimum n has to be. It has to be 1 if you are dealing with polynomials. If you happen to pick log of n as the smallest one, the largest term, you could be doing that. Make sure you start at n is 2, because n equals 1, log of 1 is 0, no matter what the base is, right? So you don't want that. All right, so now we just proved, so therefore, f of n is in big O n squared. So C equals 11, K equals 1, right? Because we have just shown that f of n is less than or equal to 11n squared. So C is the constant that I multiplied by n squared, and K is the starting number that this inequality is going to work. Now, you don't have to do anything else with functions that we give you except for get rid of sums. So if I ask you for the smallest big O estimate for a function and it's a product, and there's no sums in it, then you're done. So, for example, n squared log n, that is the smallest big O estimate for that, because there's no sums for me to get rid of, and there's no constants for me to drop. So when we did this last one, when we figured out what the function was that was dominating f, then we dropped the constant. So it was n squared that was bigger, that grew more, as long as we had a constant of 11 or more. That would work too. Okay, but what if I start doing something like this? If I multiply several functions, the big O of each of them multiplied is the same as the big O of the product. What that means is I can find the big O for each of these and multiply those big O's. I don't have to multiply it out and then find the big O. So let me write it in math. All right, so finding the big O of this is easy. The biggest term in this is n squared log n, so the big O for that is n squared log n. And by the way, a proof and just finding the big O are two different things. So for this one, I would just ask you, what's the smallest big O estimate for this? So big O for this is this, Big O for this is n cubed. Big O for the last term is n. Thank you. So the big O for the entire thing is all of that multiplied together. The last thing I would do is just combine the n's. 2 and 3 and 1 is 6. So that's n to the 6 times log n. Is that a proof? No. I just found the smallest big O estimate. The proof isn't that hard. I would separately prove that, so I don't need that. That's already like equal to that. So I would have to prove that n plus 7 is less or equal to some constant times n. And I would have to prove that n squared log n plus 1 is less or equal to some constant times n squared log n. But it's easy to do with the method we just learned. So to prove that n squared log n plus 1 is less or equal to a constant times n squared log n. You guys have a constant in mind we could use? Well, if you don't know, you do what we did before, which is replace n squared log n plus 1 with the largest term, right? 1 is definitely less than the largest term, which was n squared log n. So that inequality is automatically true as long as n is what? N is at least 2 because there's the log in there. Make sure you use a 2. Yes? That's given to you. So I'm going to be giving you functions and asking you to find the smallest big O estimate. So that would be given to you. There was nothing you know about it. I just gave you that function and said, find the big O estimate for it. Okay, so we can find the big O of each of the terms. So now we've just shown that this is 2n squared log n. So we just proved that n squared log n plus 1 has big O n squared log n with c equals 2 and k equals 2, right? And we already know that n cubed is equal to n cubed, so we can leave that in there. And n plus 7, we can do the same thing. N plus 7 is less or equal to n plus 7n, which is equal to 8n. So now n plus 7 is in big O of n with c equals 8 and k equals what? What k lets me replace 7 with 7n? 1. So if k is at least 1, I can replace 7 with 7n. So now let's just show an example of why all of this works. So I'm going to write out. So we have n squared log n plus 1 is less or equal to 2n squared log n. And we have n plus 7 is less or equal to 8n. And we have our function f of n is n squared log n plus 1 times n cubed times n plus 7. And so we know, since we know this, we could actually replace this. So we can say f of n is less or equal to 2n squared log n, and leave the other things, n cubed and n plus 7. Does everybody believe that? I've just shown, so we already know that this is true. We've already proved that. So we have to have n greater or equal to 2. That's going to satisfy the second one, so we won't have to change our starting value. And so then using this one, so we're going to use that there. Using this one, we'll leave the 2n squared log n and n cubed and 8n, and n greater or equal to 2 is just fine. And then I can combine my n's and my constants. So now I've shown that f of n is in big O of n to the 6 log n with a constant of 16 and a starting value of 2. So I'm not usually going to ask you, when I give you these multiplied functions, I'm not usually going to ask you to prove the big O. I'm just going to let you remember that the big O of the product is the same as the big O of each of them multiplied together. So I just wanted to show you how, if you can find the big O of each of the terms, then you can actually prove that the function is in the big O of the product. Any questions so far? Okay, let's look at a couple of other rules. So here's a few rules that are in your packet on page 9. This is packet 4, page 9. All right, so if you multiply a function times a constant, then it's in the big O of itself, just taking that constant off. So like 4n squared is in big O of n squared. So constants are basically disregarded. If f of x is less than g of x, then there's sum that's less than 2 times g of x, so the big O of f of x plus g of x is g of x. So basically that's saying if you have, that's what we just did actually. We just assumed that, we took the largest term, so g of x, and then we replace all the terms with that. And then we just showed that if we do that with sums, then we find that using that function is going to work as our limit. Now this third one is tricky. If a sum has more than 2 terms, count the number of terms the sum has. If the sum has m terms and g of x is the largest, then the sum is less than or equal to m times g of x. And m might depend on x. So let's look at an example of that. Okay, let's say I want to give a big O estimate for this. And I don't want any sums. Basically, whenever anybody asks you for a big O, you don't want any sums left in your answer, and you don't want any constants left in your answer unless they need to be there like they're in a power, because that actually determines how many multiplications happen. So you need to have that one. But you want to drop any initial constants. So this is actually equal to 1 plus 2 plus 3 plus 4 plus ... plus n. Does anyone want to guess what the big O of this is? Okay, I have a guess of n. Yes. Ooh, n to the n. It's definitely in that. That's a huge, huge function. Okay, so if anybody asks you for a big O estimate, you could try that one. It's probably going to work. The only thing it's even going to beat n factorial, so you're way, way over. So I usually ask you for the smallest big O estimate. It is technically right. I totally acknowledge that. But it's not super useful. Okay, so let's see about this. If I have the largest term is n, now our procedure says every time we have a sum, we want to replace all the terms in the sum with the largest one, right? So all the terms in this sum, if I replace them all with n, that would look like this, right? So I already know that this summation is less than or equal to that one, just because every single term is bigger than the original terms, right? Well, what is this number equal to? It's n times n, right? That's like take n and add it to itself n times. That's what it is. It's n squared. So this is probably not in big O of n, right? But it was a sum, and the largest term was n. So we couldn't just look at it and say the largest term is n, so therefore it's in big O of n, because Why? The size of the sum, the number of terms, depends on n. So therefore, that's a factor that we have to take into account. So that's not going to work. All right, where you did that. Now, the last rule. Any questions about this one before we go on? Does anybody not quite like this? Why do you not quite like it?
Like you're saying, it's definitely under n squared. And that's just like saying n to the n. You know it's less than that, but you haven't proved that it's less than O of n.
That's right. We actually haven't proved that it's not less than n. We've just proved that it is less than n squared. So let's try it. You were going to have to do some more math anyway, so it doesn't matter which math. Someone up here said darn, in case you were wondering. I was explaining that the torture was going to go on regardless. It's just which one you get. Okay, so let's try to prove this. Anybody got any ideas of where to start? How do you want to set the constant? You get to do that first. We need to do it first. Okay, we're gonna not pick 1. Why are we not going to pick 1? Because n is actually less or equal to n plus anything. And this is definitely something, right? Oh, we'd like to pick that c equals n, but it has to be a constant, so it can't be n. 7? Okay, let's pick 7. Does anybody know what the closed form of this is? Okay, let's divide both sides by n. That's not going to work, is it? Doesn't matter what number I put over here, this isn't going to work because eventually n will get big enough, right? Because n's allowed to grow however much. So, can't do that. Happy? Okay, happier. Now I'm going to introduce division. We're not going to do a lot of functions with division, but we might have some, so we need to look at what happens when we do. So, do you think we can take the big O of the top and the big O of the bottom and get the big O and divide those two to get the big O of this? That would be nice, right? You can, as long as your big O estimate is tight. What I mean by your big O estimate being tight is you can't get a better estimate than that. So, if I just put anything I want for the big O estimate for the bottom, it's not going to come out right. Right? If I put x to the x for the bottom, it's not going to come out. Yes? No. Big O you can always do by taking the limit as x goes to infinity. So that's like basically the definition. That's the reason why we do big O. It's actually because you can do limits. So we don't do limits because we don't need them for most of what we're doing. So you could take the limit, but we don't need to do it. What I just want to mention to you is one of the things that we do when we find big O is we find the biggest term of the sum, right? when I'm doing the top, I can totally do the big O at the top like I normally do. So this is definitely less than or equal to x squared plus x squared over x plus 1, right? All I've done is replaced a 1 with x squared. So it's definitely getting bigger as long as x is greater or equal to 1. Now, instead of replacing x plus 1 with something larger, I like to replace it with the very largest term. So it's not technically replacing it with a function that is bigger than x plus 1, but it's the same size as x plus 1. So I'm going to replace the bottom with the largest term of the sum. So if I have a sum on the bottom, I'm going to replace it with the largest term, because if I do that, then this less than or equal to holds, because the sum is definitely larger than the largest term. So I have to have that. So x plus 1 is greater than x, right? So if I divide something by a smaller number, then the number gets bigger, right? So that's like going from something over 2 to something over 3. Something over 3 to something over 2, which is definitely bigger. So you actually want to replace the bottom with the largest term of the sum, so you're actually replacing it with something slightly smaller. That's what we're doing. So when we do big O, we can do that. So now we can actually say that this is equal to 2x. So x squared plus 1 over x plus 1 is in big O of x. And we've actually just proven that, because every single one of these was a valid less than or equal to. And you should be able to tell me what C and K are when you're done with this. And they should show somewhere. So here I have my K, and here I have my C. Why don't we write down as many reasons when we do this kind of proof as we did when we did logic? It's all just math you've been doing forever and ever and ever. So that's why. So when we did logic, you weren't walking around when you were 8 going, modus ponens, my kid's not even going to do that. But you have been adding the same thing to both sides of an equation. You've been multiplying them by 2, things like that. So that's why you don't need to write down stuff. So if I thought you didn't know it, you'd have to write down more. But I assume that you know how to do basic math. I know it's sometimes wrong, but it's okay. All right, so when we have a division, just be careful about replacing the bottom with something huge. Okay, so let's look at a few functions and see if we can order them. Okay, which one out of these 11 functions is the biggest? 8. Okay, so we have a vote for 7 and a vote for 8. If you think it's 7, raise your hand. If you think it's 8, raise your hand. Yeah, the 8s win. Why? I said so earlier. You guys have a good memory. Both of these have the same number of terms, right? But all the terms in here except the last one are bigger than those. So x to the x has x terms in it, and x factorial has x terms in it. Except a whole bunch of the x factorial terms are way less than x, because they start at 1 and 2 and 3 and 4, and they're way less than x. So that's why We have 8 as the biggest, and 7 is the next biggest. What's the smallest one? I heard a vote for 2. I heard a vote for 3. I heard a vote for 6, which is the same. I actually meant that to be x log x. So we're just going to have a number 5 and no number 6. So that's supposed to be x times log x. Sorry about that. I just had variable size fonts. It was not good. Okay, so that's good because your votes are correct. So those are both smaller than x, right? Log x and square root of x are both smaller than x. The truth is, I don't remember which one is smaller. They are extremely close to each other, and the methods that I give you for doing proofs, for showing which functions are big O of each other, will not work with square root of x and log of x. So I'm not going to ask you to prove which one is bigger. I believe square root is bigger, but I'm not sure. So they're really, really close to each other. I'm not going to ask you to order them, but they're both very small. So they're approximately the same size. One of them is bigger than the other, but I don't remember which one. Somebody could look it up online real quick so we would know. Can someone do that on their phone or something? Look up which one of these is smaller. It's really hard to, the proof is really, really hard. I probably have someone proved it on Piazza last year, so I'll see if I can find that. Okay, what's the next? Yeah, we're going to have to look it up. I don't remember, and I don't want to claim the wrong thing. Log x is smaller? Yeah, so I think square root is smaller. Sorry, larger, but that should work. Okay, so that was x to the x and x factorial. Now what comes next after square root of x? Should be easy. Is it 11? Is it x squared log x? Certainly not. That's bigger than x squared, right? And x squared is bigger than x. Anything smaller than x there? No. All right, where does x cubed go? Or x log x? So x cubed is bigger than x squared, right? How about x log x? Is that bigger than x squared? Raise your hand if you think it is bigger than x. X log x. Is it bigger than x? Good. It is bigger. Log x is usually bigger than 1, right? So if I multiply x times something bigger than 1, I'm going to get something bigger. So x log x is the next thing because it is less than x squared. So I didn't put this on here, but 1 is less than log x because we're talking about when x gets large. So assuming we pick k is bigger than, say, 10 or something, this is definitely going to be true. All right, so we've got our x log x on there. We've got x squared. How about x cubed and e to the x? Which one's bigger, x cubed or e to the x? E to the x. Should be. Okay, so that's the order we have. So polynomials are less than exponentials, yes? X squared log x. Okay, so where does that go? In between x squared and x cubed. There we go. So you need to be able to do that on the test. So if I give you 4 or 5 functions, you should be able to put them in order. I'm not going to give you funky ones that have like lots of numbers in them or sums or anything. So I'll just give you basic ones like this for ordering purposes. If you forget, like if you look at a log and you're in a test and you freak out, just remember that log x is bigger than 1, and then start multiplying both sides of that equation by stuff until you get what you want. So if you forget whether x log x is bigger than x or not, divide both sides by x and then see what you get, and that makes sense. That log x is bigger than 1, so start checking some values for that. Any questions? Yeah, so we can have functions that are log x quantity squared, but I'm not usually going to ask you to order them. So you can have that as a big O. I mean, it does happen, but I'm not going to ask you to order it because it's like, I don't know how big that is. Okay. So now we're going to look at a couple of more definitions. So in your homework is going to ask you about a couple of more functions that you need to know that are related to big O, and they're very similar. So the next one is called big omega. And an omega looks like that. And the definition is exactly the same as big O, except for you switch the less than or equal to sign to a greater than or equal to. And I'm going to leave off the absolute values because, like I said, we're not going to work with negative functions. So big omega, so f is in big omega of g if this is true. So that definition is the same. So that equation and this statement mean the same thing. So this is like the opposite. So if f is in big O of g, it is definitely not going to be in big omega unless they are approximately the same size. So if f is in big O of g and g is in big O of f, then f is in big theta of g. So big theta is the set of all functions that are approximately the same size. So they grow at the same rate. So I'm not going to ask you to prove that anything is big omega or big theta of something. I might just ask you to show that something is big theta of something else. So if I'm going to show that something's big theta, I have to show big omega and big O. So let's do an example. So if I want to show that 10x squared plus 100 is in big O of x squared, I first am going to show that f of x is in big O of x squared. So 10x squared plus 100 is less than or equal to 10x squared plus 100x squared, as long as x is greater than or equal to 1. And this is equal to 110x squared. So now we have f of x is definitely in big O of x squared with c equals 110 and k equals 1. So now I have to show that f of x is in big omega of x squared. So what I want to find now is a lower bound, and the easiest way to find a lower bound for the sum is just to take the biggest term and drop everything else in the sum. So now we've actually just proven f of x is in big omega of x squared. Sorry, that's not a very nice one. C equals 10 and k equals 1. So what we've just done is we've actually bounded 10x squared plus 100 on the top and on the bottom. So on the bottom, it's bounded with 10x squared, and on the top, it's bounded with 110x squared. So what that would look like on a graph is that I could draw all those functions, and if I draw 110x squared, it'll always be above this one, and if I draw 10x squared, it'll always be below it. So I've sandwiched my function in between those two, and therefore they grow at very similar rates. So it's super easy to show that something's in big theta if it actually is. So it's really not hard to do. If it's a sum, you just, to show big theta, big omega, you just drop all the terms except the largest one. Okay, so I'm going to give you a few functions, and then we're going to figure out if they're in big omega, big theta, or big O of each other. All right, so in our first row, we have 1700x plus 20,000. Is that in big O of x squared? So when I ask you if something's in big O, can I bound it by a constant times x squared? Is it less than or equal to some constant times x squared? Yes. So is it in big omega of x squared? No, because they are not approximately the same size. So it can't be in the theta. So if we can, let's also write the smallest big O estimate. So the smallest big O estimate for this is big O of x, right? All right, x log x plus 17x plus 1. Is that in big O of x squared? Yes. Because the largest term is x log x, and that is less than x squared, which we already talked about before. And the smallest big O estimate is x log x. How about x squared log x? Is that in big O of x squared? No, it isn't. Is it in big omega of x squared? Yes, because I can prove that it's bigger than x squared as long as x is big enough. And it can't be in big theta unless it's in both. How about x squared plus x cubed plus 3? Is that in big O of x squared? No. Is it in big omega of x squared? Yes. And it's not in both. So how about, can you make up a function that is in big theta of x squared? X squared plus 1? Yes. So it's in all three. So those are the smallest big O estimates for those. So we've already done the kinds of things that you have to do on this homework for big O. The last thing that you'll have to do occasionally is to do a proof, an induction proof, to show that one function is smaller than another one. So let's do one. So let's prove this one that we weren't certain about to begin with, that n squared is less than or equal to 2 to the n. And we're going to do it by induction, because that's how we prove things that need to be true as n goes to infinity. So what do we need to start with? Is 1 going to work? If we put 3 in here and we put 3 in there, we get 9 is less than or equal to 8. So let's start with n equals 4. Okay? So we're going to get 16 is less than or equal to 2 to the 4th, which is 16. All right, now, this is where, when we have an inequality, this is where it gets a little bit different than what we do for equals. So there's a magic step in proofs with inequalities. And I'm not like Dr. Bitzer, I can't do magic tricks. But I can do magic steps in math. I used to teach with him, and he taught me how to do the magic tricks, but I would do them for class, and then people at the end of the trick would go, I saw you do that. I can't do them. So I know it would be entertaining if I tried, but it's not going to work. Okay, so, but we do have some magic steps. So the first thing we need to do is figure out which one of these sides would I like to start with. So I have to start with the assume. You know, we always write down one side of the prove, set it equal to the same side of the assume. But it looks much easier to deal with going from 2n to 2n plus 1 than it looks to go from n squared to n plus 1 squared, right? So I'm going to start with the right-hand side. So I know that's different than what we did before, but I always want to start with whatever's easiest. So the right-hand side's easier because I can just multiply it by 2. So 2 to the n plus 1 is equal to 2 times 2 to the n, right? And that's the right-hand side of the assume. And this is the right-hand side of the proof. Now, since that's on the right-hand side of the assume, I want to replace it with the left-hand side of the assume, just like we did in our equality proofs. But we can't put an equals. We have to put the proper less than or equal to or greater than or equal to sign. Which one is it? If you think it's greater than or equal to, raise your hand. If you think it's less than or equal to, raise your hand. If your hands are busy writing, raise your hand. Yes. I messed up. That's what I did. No wonder nobody voted for the right thing. Okay, so is it a greater than or an equal? Less than. Raise your hand if you think it's greater than or equal to. Raise your hand if you think it's less than or equal to. Okay, it's greater than or equal to because I'm here and looking at that. So if I want to replace the right-hand side of the assume with the left-hand side of the assume, I'm getting smaller, right? So I have to have this. That's good because that's what direction I need to go. So now I have 2 to the n plus 1 is greater or equal to 2n squared. And I want 2 to the n plus 1 is greater or equal to n plus 1 quantity squared. So here's the magic step. The magic step is if I were to have 2n squared is greater or equal to n plus 1 squared, then I could get this, right? So if this is true, then we'll get that. Because greater than or equal to works like implication. It's transitive. So if 2 to the n plus 1 is bigger than 2n squared, and 2n squared is bigger than n plus 1 quantity squared, then I would have that 2 to the n plus 1 is bigger than n plus 1 squared. Right? So basically I'm getting an intermediate value. So this is what we call the magic step, is that you come up with what this equation is. It's not hard, and most magic tricks aren't that hard. It's just hard to get people not to see what they were. That's the hard part that I can't do. Okay, but this part is not hard once you know what you have to do. So I'm trying to prove this. I have this based on the assume. I multiplied 2 by both sides of the assume to get that. I want this. I don't have it. So let me guess that the right-hand side here is bigger than what I finally want. And then I need to do a proof for that. So now we need to do some algebra on this. So we're going to multiply out. So I don't actually know yet if this is true. So I like to put a little question mark over it. So we multiply it out. Let's subtract n squared from both sides. And at this point, I usually also divide both sides by n. Is that going to be true? Yes, because 1 over n is always less than or equal to 1. And n is greater than 4, so this is fine. And we could divide both sides by n because it's never 0, so it's okay to do that. So I do finally say, since 2 to the n plus 1 is greater or equal to 2n squared, and 2n squared is greater or equal to n plus 1 quantity squared, then 2 to the n plus 1 is greater or equal to n plus 1 squared. Okay, well, that is all for today. Thanks very much. Start your homework 7.